This presentation is about Calgary's inundation model and its application to Project Denver flood risk. In 2013, Calgary experienced a major flood. The estimated damage to the city and property and infrastructure was about $500 million. The purpose of this project is to create a predictive model based on the data of Calgary and use this model to predict flooding in Denver. The goals of the projects are as follows: to adopt a scientific approach studying and predicting natural disasters, to assist policymakers in the environment and infrastructure section, and to protect assets and finance of local residents. Now the methodology for the model is as follows. Determine a city for comparison, that we select Denver, then collect data for Calgary and Denver, and then do feature engineering and create fishnet by the size of 300 by 300 and put the features into the fishnet and then export it from GIS and import it to R. Then run forward and backward selection for non-multicollinear criteria and run logistic regression for significant factors and training and testing, and then predict the model on Denver and validate the model to determine accuracy and generalizability of the model. We selected 3 different types of variables: geographical, spatial, and hydrological. These variables as follows have been put on fishnet to determine their association with flood in 2013. Based on the plots bar, we are able to show the differences in independent variables between inundation and non-inundation. In the first step, we consider flood accumulation as the dependent variable to run the backward selection to eliminate multicollinear variables. But as the result, we decided to continue with all variables. The next step for our model process is to split data randomly into 70% training set and 30% test set, and then build the model on training set and validate the model on test set. The dependent variables for our regression model is flood inundation. As a result of logistic regression, we can see that the variables are statistically significant in our models at a 90% confidence interval, except for 4 variables: tree density, flow accumulation, basin, and flow length.
Then we ran the model on the test sets. The predicted probabilities of most locations are below 0.15. The distribution of both flooding and non-flooding probabilities shows that our model performs better in predicting non-inundation areas than inundation areas. The AUC curve reveals a 0.96 accuracy of our model. The model did well in both the true positive fraction, which means areas predicted to have flooding and actually suffered flooding, and the false positive fraction, which means areas predicted to have flooding but not suffer flooding. Sensitivity, which means correctly identified flooding areas, is 0.40, and the specificity, which means correctly identified non-flooding areas, is 0.99. Cross-validation presents a 0.9650 accuracy. As observed, the predicted flooding map fits in the trend of the actual flooding map, while presenting a larger coverage with both severely and mildly affected areas. This is because our model is based on many hydrological variables. The observed flooding map, however, was much simplified in the process of generating fishnets. We tested the model on Denver. First, we used the Calgary model for Denver, and the result wasn't satisfying, and then we went through the whole process again for Denver with the same set of spatial characteristics. The result was impressive with an accuracy of 0.9998. In conclusion, the predictions using the model generated from the same city are well formulated. The prediction using Calgary model predicting Denver failed. In the future, more variables such as soil condition, annual rainfall, and more specific environmental features like land cover can be added with this analysis. And thank you for listening.